Hello everyone, welcome back. In this lecture, we are going to discuss on process planning of parts, process planning of assemblies and bill of materials, commonly known as BOM. We will learn how manufacturing plans are developed for individual components, how multiple parts are assembled into a final product, and how BOM serves as an essential document for manufacturing and inventory management. Now coming to the process planning of parts, the process planning of parts begins with understanding the material and design requirements. The product designer first select a material based on functional requirements such as strength, durability, thermal resistance and cost. So common engineering materials includes metals, plastics, ceramics and composites. Each material category has a specific manufacturing constraints and opportunities. So the material influence on process selection is very much in manufacturing process. So the selected material can be processed using casting, forging, machining and welding. So the plastics are commonly manufactured through injection molding, extrusion and additive manufacturing. So the composite materials required specialized techniques such as layup, molding or filament winding. So material properties like hardness, ductility and melting temperature directly affect the process selection. Coming to the influence of the part design. Part design further refines the manufacturing plan. Dimensions, tolerances, surface finish requirements and geometric complexity determine which manufacturing methods are very much suitable. Complex shapes requires CNC machining or additive manufacturing, while stringent surface finish requirements may necessitate secondary operations like grinding or polishing. So a typical process planning sequence of parts begins with selecting the raw material. This is followed by the primary manufacturing process such as casting or forging. Secondary operations like machining are then performed. Additional treatments may be applied to improve the mechanical properties, followed by finishing operations such as polishing, coating or heat treatment. Now the final output is documented in the form of a root sheets as shown in the figure. Okay, so root sheet consists of all the details like part number, part name, the page numbers and what is the material, what is the size of the material, who is the planner and when the process plan is being manufactured, and it also includes the sequence number, what are the operations to be carried out and which department it has to be sent and which machine the operation has to be performed, the tooling gauges, setup time, cycle time, etc. Right. Next, so the basic process concept. The basic processes refers to the primary manufacturing method that creates the initial shape of the component. Examples includes casting, forging, rolling, extrusion and molding. So the choice of the basic process depends on the material properties, production quantity, geometry and cost considerations. So coming to the process planning for assemblies. So unlike individual parts, assembly process planning deals with combining multiple components into a functional product. So this is inherently more complex because it must consider interactions among components, assembly methods, tooling requirements, quality control measures and overall product functionality. So coming to the types of assembly planning. Assembly planning differs according to the production setup. So in a single station assembly, one worker or a team assembles the complete product at one location. So in assembly line production, tasks are distributed among multiple workstations requiring careful planning and workload balancing. So the single station assembly planning is commonly used for low volume or customized products. The planner first lists all assembly steps, identifies critical operations, determines tooling requirements, optimizes the assembly sequence and integrates the quality checks throughout the process. So coming to the assembly line process planning, So the assembly line production is suitable for high volume manufacturing. So the process begins by defining individual work elements and calculating the number of stations required. So workloads are then distributed evenly among the stations through line balancing, and the resources are allocated appropriately. Workflow is optimized to minimize the ideal time, and inspection points are incorporated into the production line. So coming to the line balancing and takt time. So line balancing is the process of evenly distributing work among the workstation to minimize the bottlenecks and improve efficiency. An important concept here is the takt time. So which is nothing but the rate at which the products must be produced to satisfy the customer demand. So proper line balancing ensures that production matches takt time and prevents delays or excessive ideal time. So coming to the differences between the single station single station versus assembly line comparison. So single station assembly focuses on detailed tasks performed at one location, and it is suitable for low volume production, whereas the assembly line production distributes tasks across multiple stations and it is ideal for high volume standardized products. So each approach has its own advantage depending on production requirements. So now we will go to the topic bill of materials. Commonly it is known as BOM. A bill of materials is a comprehensive list of all the raw materials, components, sub-assemblies and parts required to manufacture a product. So it serves as a blueprint for manufacturing by specifying quantities, material specifications and other essential information required for production planning and inventory control. Coming to the key components of the bill of materials. So a bill of material contains several key elements, includes the product descriptions, item numbers, quantities, unit of measurements, specifications, drawings, drawing numbers and supplier informations. So there are four major types of BOM. They are engineering BOM used during product design, manufacturing BOM used during production, sales BOM used for marketing purposes and service BOM used for maintenance and repair. So coming to the benefits and examples of the bill of materials. So the handheld electrical drill example demonstrate how every component is systematically documented. So BOM offers numerical advantages including improved inventory management, accurate cost estimation, better production planning, enhanced quality control and effective communication between the departments. So this is the example for hand-held electrical drill example, which is mentioned before. Okay, so you can see these are the bill of materials. What is the part number, part name, material, specification, quantity, unit, remarks, okay, which is required for producing a handheld electrical drilling machine. So these are the entire specifications required for preparing the bill of materials. Coming to the uses of the bill of materials. Throughout a product life cycle, BOM supports compliance, maintenance upgrades, vision control and collaboration among the engineering, procurement, manufacturing and quality team. Right. So to summarize, process planning of parts and assemblies ensures efficient manufacturing, while bill of materials acts as a backbone of production planning by organizing all required information in a structured manner. So with this we wind up this session. Thank you all. We'll meet in the next session.